Hey guys, the objective of this video is to understand consolidation and see the relationship between the total stress, the effective stress, the excess pore water pressure, and the settlement. So the examples we've been doing so far, we've been looking at a profile of soil at any point under the surface, and we've been finding the settlement, say, as 20 millimeters. Now this settlement is in the long time future. It takes a long time to get this final settlement of 20 millimeters. So this is a final settlement. But settlement occurs over time, which is what consolidation is. Consolidation is when settlement occurs over time. So we're going to be looking at a quick model to understand this. And the main function of consolidation is something called excess pore water pressure. So not pore water pressure, but excess pore water pressure. And we're going to see what that means now. So say we have a sample of soil in a container. And now this container has a tap at the top, which I'm going to close for now. So there's a tap there which we can open and close. So it's closed now. So this is, say, stage 1. Now at stage 1, let's say we are at a point, okay, so we have solid particles, and we have water particles and air particles inside our sample of soil. Now as we come, okay, so let's look at a point A. So A is any arbitrary point within inside the system. Let's say that the total stress is 60 kPa, the pore water pressure is 10 kPa, and the effective stress is 50 kPa. Once again, the total stress is a addition of the pore water pressure plus the effective stress, where the effective stress is what the soil particles are actually feeling. Now, this is at stage 1. At stage 2, we come and we put a load onto our system, right? So we have induced a pressure. Let's say the pressure is 20 kPa. So we've put a pressure of 20 kPa on our system. So this is stage 2. Now, what happens is, at this stage, is that the soil particles don't actually take any of the load. It's the water particles which take all the load. So we have a build-up of water pressure, and we call that excess pore water pressure. So we have a change in the pore water pressure of 10 plus 20, so 30 kPa. The total stress has increased to 80 kPa, and the effective stress, the stress that the soil feels, is still the same, 50. So what's happened is that the soil has not taken any of the load, but it's the water which takes all the load in the beginning. What you'll also notice is that we've got an immediate settlement. This might be very small, but we have some type of immediate settlement. Okay? So what's happened is that we've applied a load and we've got an excess pore water pressure. So we have an excess of 20 kPa pore water pressure because all the pressure goes to the water and none of it goes to the soil. But what's going to happen is, over time, we're now going to come and open up our valve or our tap. So our tap's now open, and the excess pore water pressure is going to start escaping. So this is now going to lower down further as the excess pore water pressure escapes. So let's say at this stage the total stress is still 80 kPa. That does not change throughout the entire process because this load is not changing. The pore water pressure, let's say, is now equal to 20 kPa. So originally 30, it's 20. That means that our excess pore water pressure has reduced by 10 to get us to 20, which means that our effective stress is now 60. So you can see that from this stage 2 to stage 3, as our excess pore water pressure escapes, more of the soil takes the load. So the soil was initially taking 50, but now it's taking 60 as excess pore water pressure escapes. And then we finally get to stage 4, where all the excess pore water pressure is escaped, not the actual pore water pressure, but the excess pore water pressure has escaped. We still have water particles, which is what we initially had of 10 kPa. So at stage 4, we have a total stress of still 80. The pore water pressure now is back to 10, right? So you can see that we went from 10 to 30 to 20 back to 10. So we have no excess pore water pressure now. All the excess pore water pressure is gone. We still have the original pore water pressure of 10 kPa though. And now our effective stress is 70 kPa. So you can see that the soil is doing even more work now as more excess pore water pressure escapes. So this all, and once again we'll get further settlement. So this all occurs over time. So at time equals 0 to time equals infinity. And the reason this takes time is, say for example you have clay. So we have a section of clay. So clay has very fine particles. And when we say put a foundation on the clay, so we put a foundation, so we put load on our clay, we're going to get a build-up of excess pore water pressure because of this load, and this pore water pressure takes time to escape. Because the clay particles are so fine and so close to each other, it takes time for the water to escape, which means that we're going to get a change in settlement with respect to change in time, where at time equals infinity, all the excess pore water pressure will escape, and we're going to get our maximum settlement.